Hello, we are Triton AI team working on simultaneous localization and mapping for an electric go-kart. I'm Alexandra and I'm computer engineering undergraduate major, and my partner is Ashish and he is graduate student majoring in computer science and engineering. Throughout the quarter, we worked on this project along with a few other members of Triton AI team participating from other classes. The main goal of this project was to enable an electric go-kart to race autonomously without previously knowing the racetrack. The path to follow was marked by traffic cones spaced 9 feet apart, and to enable the go-kart to race within the path, we needed to be able to recognize the cones and obstacles. Moreover, we needed the go-kart to effectively localize its own position and map the track to increase the speed on the next lap. The first task we focused on was detecting cones and obstacles. Next, we retrieved LiDAR point cloud to enable depth perception and object clustering. Lastly, we needed to fuse the two to be able to recognize the traffic cones and reliably tell how far they are from the go-kart at any moment. All data retrieved from the camera and LiDAR was sent to an AJX computer for processing. As a result, the go-kart was able to recognize the cones and tell how far they are. That information was the key to localizing its own position and planning the best path to follow.
For object detection using the camera, we trained a machine learning model using computer vision and YOLO Wi-Fi on datasets available on RoboFlow to detect cones with the help of bounding boxes on image frames. Utilizing the stereo camera on the evG Pro, we extracted the depth information of the detected cones to calculate the relative positions. Using the cone positions and the IMU sensor on the camera, we calculated the heading direction and built a map for path planning. With the help of an algorithm developed by a team in TU Berlin for Formula Student Driverless, we created a racing line for our evGoKart to follow. Here, we can see that the object detection model can detect cones in a controlled environment in the lab, but when deployed on field, we observe that the RGB and the depth frames of the camera are not aligned. The bounding boxes in a depth frame don't capture the cones correctly, resulting in unreliable depth perception. This affected our mapping and path planning framework, leading to inaccurate race lines. Hence, we switched to LiDAR. The tasks involved here were to get the point cloud data of the surroundings using ROS2 drivers for the LiDAR. Next, perform object clustering to find the cones and determine the relative positions. This part was performed by the other members of the Triton AI team during the AKS race event week at the Purdue University. Once the cone positions are known, we gave them to our path planner to create the race line. Here's a small demo. We have a LiDAR ROS back to simulate point cloud data of the racetrack. You can see that as we move along the track, on the top left of the video, we show the instantaneous map of the cones lying ahead of the evGoKart and the race line it needs to follow. We are also able to map and show race lines for turns along the track. Next, we move on to the challenges.
There are several challenges that significantly impacted our work. The first one, and probably one of the most important ones, was lack of LiDAR knowledge. No one on the team had any previous experience with LiDAR, so we ended up just learning things as we went. Second, almost as challenging, was camera calibration. Because evG Pro is a wide-angle camera, the images were distorted to a fisheye view. We needed to calibrate it to output a straight image that LiDAR point cloud could be mapped on. Similarly, due to the image distortion, we were not able to get a reliable camera depth and needed to rely more heavily on LiDAR. Lastly, most of our project needed to be done a few weeks earlier to be able to use it during the race in May. That gave us a significantly shorter timeline. Next year's race will use only the wide lanes to mark the racetrack, and that lane detection is what we will be focusing on in the future. We are also working on transferring all our autonomous driving algorithms from the large size go-kart to a 1/5 size model. This requires making adjustments for hardware with different specifications. Thank you.